Welcome to Physics 30 Prep Fast Track, Lesson 3.5, Work and Energy. C, we're going to now talk about conservation of mechanical energy using some examples where we have kinetic energy being turned into potential or potential into kinetic in an ideal system. So, in an ideal system where friction is negligible, we say that mechanical energy is conserved in its two forms. And those two forms, of course, are kinetic energy, which is 1/2 mv squared, and potential energy, which is mgh. The system starts with a certain total energy due to either its motion or its position. So, for example, a swing at the playground is a good example of a mechanical system where the energy is either, if the swing is moving fast near the bottom, it's lots of kinetic, or if it's near the top, then it has potential. And if we ignored the friction that the rider was experiencing, we could say this was an ideal mechanical system. And the energy is converting back and forth. So the total energy is always the same. So if you give somebody a push and then you walk away, you've given them a certain amount of total energy to start with. And that total energy can be either kinetic or potential. And of course the kinetic energy, the formula for kinetic energy is 1/2 mv squared, and for potential mgh. So the total has to be the sum of those two. So if the total is always the same, then a loss of kinetic would result in a gain of potential. Once you've gone through the equilibrium position at the bottom and you're starting to go up, you'll have lots of kinetic energy at the bottom, and as you rise, you gain height and therefore you gain potential. Where did that potential come from? Well, you're also slowing down as you get higher and higher to the maximum height. And of course, at the maximum height, you stop. That means you've got zero kinetic, but lots of potential. So a loss of kinetic would result in a gain of potential, and vice versa. A loss of potential would result in a gain of kinetic. The sum would remain constant because we assume with this swing set that no energy enters or leaves the system because friction is ignored. So let's look at an example. In the first example, a cart with a mass of 10 kilograms with frictionless wheels rolls down an incline, and it is a closed system because I said frictionless incline. So it's a closed system. That means the potential and the kinetic, the sum of those two will always be constant. And they're giving you the height of the incline. What's the speed of the cart? So we can say at the top of the incline, we have lots of potential energy, and as the cart slides down the track, it will lose potential energy but gain kinetic energy. And so we can use that idea to solve for the velocity or the speed at the bottom. So we say the total energy is kinetic plus potential. E total is 1/2 mv squared plus mgh. Now, since the initial velocity is 0, the kinetic energy at the top is 0. So in the initial state, all the energy is potential. And therefore, the total energy is the potential is equal to mgh. Now, as the cart rolls down the ramp, it loses height, which of course is a component of potential, but it gains speed, which is kinetic. So your potential energy is turning into kinetic. At the bottom of the incline, all the energy will be kinetic because the height will be 0. So there won't be any potential at the bottom. All of that energy will have turned into kinetic energy. And so we can say that the total energy is equal to the maximum potential at the top, and it's also equal to the maximum kinetic at the bottom. And that gives us this interesting idea here, where the total energy can be the maximum potential or the maximum kinetic, and therefore if you say that these two are equal, potential max and kinetic max are equal, then mgh at the top is equal to 1/2 mv squared at the bottom. And that leads us to a solution. Once we take this relationship and solve for v squared, we get v squared is equal to 2 mgh over m, or in other words, if the m's cancel, then we get 2gh. So v squared is 2gh, and 2 times 9.81, of course, we're using gravity, times the height of the ramp, not the length, but the height, gives us 29.43. When we take the square root of that, we get 5.42 meters per second. So the ramp, at the top of the ramp, the cart had zero velocity but lots of potential due to its height. As it slid down the ramp or rolled down the ramp, at the bottom it has no potential, but it has it has an equivalent of 5.42 meters per second, and that's what gives it the same amount of kinetic energy. All right, so it started with a certain amount of potential. Now it's got a whole bunch of kinetic, the same amount. You'll notice in this example that the mass of the cart was not used. This implies that no matter what the mass of the cart, whether it's a heavy mass or a light mass, the speed at the bottom would be the same. And of course, Galileo apparently had the same idea. He took a large cannonball and a smaller cannonball and dropped them both from the Leaning Tower of Pisa, and they both hit the ground at the same time as he had predicted. We don't know whether he really did this or not. But an alternate method for example 1 would be to use the mass and height to figure out the potential at the top. So you could have said, what is the potential when we started? And of course it works out. If the mass of the cart was 10 kilograms, then you would multiply that by 9.81 and of course by its height and get 147 joules. Now as that cart rolls down the ramp, that 147 joules of potential turns into 147 joules of kinetic. And so now you know that the total energy, which is the maximum kinetic now, is equal to 147, and therefore when you take your formula for kinetic energy, which is of course also equal to 1/2 mv squared, and solve for v, you first get v squared is equal to twice the kinetic energy divided by the mass. When you substitute that, you get again 29.43, just like on the previous page. The square root of 29.43 is 5.42. So at the bottom of the ramp, the cart is moving 5.42 meters per second. Now notice we did this once with the mass, and then we, by equating the two formulas, we actually cancel out the mass, so the mass doesn't matter. So even if you did this with a different object with a mass of more than 10 kilograms, if you doubled it at this point, at some point later on you're going to divide that by 2 or by that doubled amount, and that increasing by a factor of whatever and then decreasing by the same factor, they cancel up. And so the previous example is actually a little more of an elegant solution, but this way works too. So let's look at an example of elastic potential energy. We'll talk about an archer pulls on a bow with an average force of 65 newtons over a distance of 1.3 meters. She then points the bow straight up and releases a 0.35 kilogram arrow. How high will the arrow rise, and how fast is the arrow moving when it hits the ground? Now, this is a fairly complex question. Here are the two solutions. What you may like to do, if you're feeling confident, is see if you can figure these two answers out on your own. So stop the tape and try these. If you're not feeling overly confident, you might want to watch the example. But it's a good idea to try it on your own. The answers are there, and if you get it right, then you can move on. Anyways, using conservation of energy, the initial work done by the archer is Fd, because she's applying a force over a distance, and that's giving the bow and arrow system elastic potential. And so, of course, the work that she's doing is 65 newtons times 1.3 meters. She's given the bow 84.5 joules. And if we assume that this is an ideal system, then this is the starting energy of the system. So in question A, when we ask how high will the arrow rise, well, you have to remember that if the arrow starts at ground level, if the arrow starts at the bottom and it has 84.5 joules, what's going to happen as it rises? Well, that elastic potential is turning into gravitational potential. Then what happens as the arrow comes back down, that gravitational potential is turning into kinetic energy, and that's how we'll answer B. But in the first question, it says how high will it rise, so we need to know what H is at the top. And that, of course, will be due to the fact that when the arrow is released, it has 84.5 joules of kinetic energy. And the kinetic energy turns into gravitational potential energy, and at the top, only potential energy will be present. And so, since the potential is equal to mgh, since we solve for h, since we want to know what the height is, we multiply, or we divide both sides by mg, and so we get the potential energy divided by mg, or in other words, the elastic potential at the bottom turns into gravitational potential at the top. We divide that by mg, and we get 24.6 meters. That is the height that that arrow will reach. Now, of course, we are assuming that friction is ignored. There's a good solution. So, in order to solve for B, we can again use conservation of energy. The initial work done is FD 84.5. So, when we solve for B, when the arrow is released, it had 84.5 joules of kinetic energy. The kinetic energy when released will be the same when the arrow hits the ground. And so, as it rises, it has 84.5. When it comes back down, it has 84.5. And so we can say that the kinetic energy is 1/2 mv squared at the bottom. And solving this relationship right here, solving for v squared, we get 2 times the kinetic energy divided by the mass. Again, 2 times 84.5 divided by 0.35 gives us 482.9. But of course, remember, that's v squared. And so we take the square root of that to get the final velocity or speed of the object when it hits the ground, and it will be moving at 22.0 meters per second. So that's the speed when it left the arrow, and that's or left the bow, and that's the speed when the arrow hits the ground. So those are the kinds of questions you'll be looking at using conservation of energy ideas. All right, elastic potential, gravitational potential, and kinetic energy. We'll touch on that. You'll touch on that a little more deeply in the 30 class.